Good day everyone, I'm Proelanuel de la Torre and I'll be presenting the linear transformation, theorems and application. Let's begin with an introduction to what linear transformation is. A linear transformation is a function between two vector spaces that preserves two key operations, vector addition and scalar multiplication. This means that for a transformation T, if you apply it to two added vectors or scaled vectors, it behaves consistently with the operation of the space. So now here's the definition. Let's define some important concept. First, the transformation T maps from vector space B to vector space W, written as T V to W. For T to be the linear, it must satisfy T times the quantity of U plus B is equals to T times U plus T times the quantity of B and T times the quantity of CU is equals to CT times the quantity of U. We also have the kernel of T, which is the set of all vectors V in V such that T times the quantity of V is equals to 0 or T to V is equals to 0. The image of T, which is the set of all vectors W in W that result from applying T to some vector in V. So let's proceed in the key theorems. Here are some essential theorems. The rank nullity theorem tells us dim ker T plus rank T is equals to dim V. A transformation is one-to-one if the kernel contains only the zero vector. It is also into if its image covers the entire codomain W. Also, the composition of two linear transformation is still linear provided both are linear. So, moving forward, here is the application. Linear transformations are not just abstract. They have many real-world applications. They help solve system of linear equation. Also, in computer graphics, they perform scaling, rotating, and transforming images. Also, in machine learning, data transformation rely on linear maps. In differential equation, linear operators are used to find solutions. While in physics, coordinate transformation make calculation more convenient. So here is the example 1, T r squared to r squared. Let T, so x and y, is equals to 2x 3y. We can show this is a linear transformation because T times the quantity of U plus B is equals to TU plus TV. And T times the quantity of CU is equals to CT times U. It behaves just like we expect from a linear function. So here is the example 2, kernel and image. Now for a more detailed case, let T map r raised to cube 2 raised to 2 r squared defined by T times the quantity of x, y, z is equals to x plus y and y plus z. The kernel of T is the set of vectors that map to 0, which here is span to -1, 1, and -1. The image is the span of vectors 1, 0, and 1, 1. So the rank is 2. So to include linear transformation are essential in understanding how vector space interact. They have broad application across math, science, and engineering, and are so powerful tool for analyzing and solving complex problems. That's all. Thank you.